Today we'll be discussing concentration, its applications in various fields, as well as we'll be performing a number of calculations that are used to measure concentration in a number of different ways. So first of all, what is concentration? It is the measure of a number of particles of the solute that are dissolved in the solvent. A concentrated solution is going to have a large number of particles of the solute dissolved within the solvent. As you can see here, the red solute particles are dissolved in the solvent, which in this case seems to be water, and there are quite a large number of those red particles. However, a dilute solution will have a small number of particles of the solute dissolved in the solvent. If we have a look at the diagram here, there are much fewer red solute particles dissolved in the same volume of water within this beaker. So why use concentration calculations? They can be used in a number of different fields, including analytical chemistry. That might include forensic chemistry, commerce and industry, in order to work out if it would be, for example, viable to extract a mineral from a particular ore, or environmental chemistry, to measure the contamination in particular waterways or in the air. So what are our different types of concentration calculations? The first one we'll be looking at is percentage composition. You can calculate percentage composition using a number of ways. The first is by mass. That is represented by a percentage W on W, which means weight over weight. This is not really named correctly as we are calculating the mass of the substance versus its weight. So the percentage W on W is calculated using the mass of the solute in grams, divide that by the mass of the total solution, also in grams, and timesing that by 100 to get the percentage. Percentage composition can also be calculated using volume or percentage V on V. And that's using the volume of the solute in milliliters, where we might have a solute in liquid form, for example, over the volume of the solution in milliliters. And we would also times that by 100 to get the percentage. Another type of concentration calculation is mass in a volume, in a particular volume. In this particular instance, grams per litre. So we would be looking at calculating the mass of the solute in grams and dividing that by the volume of the solution in litres. Another way to measure very, very small concentrations is to look at parts per million. The first way is by mass. So parts per million, or ppm, can be calculated using mass of the solute in milligrams and dividing that by the mass of the solution in kilograms. Note that 1 kilogram is equal to 1,000 grams and that 1 gram is equal to 1,000 milligrams. So if we convert kilograms into milligrams, we would have 1 million milligrams. So if we had 1 milligram over 1 million milligrams, we would have 1 part per million. You can also calculate parts per million by volume. So parts per million would be calculated using the volume of the solute in milliliters over the volume of the solution, this time in kiloliters. So 1 kiloliter is equal to 1,000 litres, and 1 litre is obviously equal to 1,000 milliliters. So once again, converting kiloliters to milliliters gives you 1 million milliliters. So that's how we get the value over 1 million. Let's look at a few examples to see if we can use these particular calculations. The first one, 12.5 grams of cordial is dissolved in 75 grams of water, and we're calculating the percentage composition in mass. So the mass of the solute is 12.5. The mass of the solution would be the mass of the solute in this particular instance, because it is a liquid, plus the mass of the water, the solvent, in order to get the total solution. So in order to work this out, we would then go 12.5 divided by 87.5 times by 100. And that would give us a percentage of 14.2. In order to work out the significant figures, we look at the two values. 12.5 has a significant figure value of 3, whereas 75 has a significant value, figure value of 2. So we would go with the smallest number of significant figures. Therefore, we round up to 14%. We've got the answer there already, but that's okay. We'll go through the working here. A cordial water solution was made up to a concentration of 23.6% weight on weight, or by mass. If the final mass of the solution is 500 grams, what mass of cordial was added to the water? So in this particular instance, we'd have to rearrange the equation. So we'd input 23.6% is equal to the mass of the cordial over 500 times by 100. So the mass of the cordial is then equal to 500 by 25.6 divided by 100, which is equal to 118 grams of cordial that was required to add. Now we're looking at parts per million. A sample of tap water contains 0.0652 grams of mercury per 250 grams of solution. Calculate the concentration of mercury in parts per million. So in this particular instance, the mass of the solute must be converted to milligrams, as previously stated. So we need to times this value in grams by 1,000 to get the number of milligrams. So we have 65.2 milligrams of mercury. The mass of the solution in kilograms must then be converted from grams, and that gives us a value of 0.25 kilograms. So the part per million then calculation is simply 65.2 divided by 0.25, which gives us 260.8 parts per million. And that would be a lot of mercury in a solution, and we would probably recommend that we don't actually consume that tap water. Now we're going to be looking at another concentration, and that involves our beloved moles. Okay, so for chemists, the most convenient and commonly used measure of the concentration of a solution is the molarity of a solution, where the concentration is equal to the number of moles of solute, which we can obviously work out from mass, knowing that the number of moles is equal to mass divided by molar mass, over the volume of the solution measured in litres. That's absolutely must. So therefore our unit becomes moles on litres, or moles per litre. Examples of these molarity calculations. So this one here is asking us to calculate the molarity of a solution that has 0.2 moles of solute dissolved in 400 mils of the solution. Using our equation, this is sometimes summarized to C equals N divided by V, where the concentration is equal to number of moles of solute over the volume of the total solution. In this particular instance, the concentration is then equal to 0.2 moles divided by the 0.4 litres. I've converted from the 400 mils. The concentration is equal to then 0.5 moles per litre. Another example. Calculate the volume of a 0.5 mole per litre solution that contains 0.025 moles of solute. So in this instance, I've rearranged the equation to show that volume is equal to the number of moles divided by concentration. So the volume is then equal to 0.025 moles divided by 0.5 moles per litre. So the volume in litres is then 0.05, or 50 mils. What happens when we dilute solutions? So when a solution is being diluted, it generally means that more solvent is being added. So therefore, the number of moles in the solute from the original solution does not change. Therefore, the number of moles in the original solution would be equivalent to the number of moles in the diluted solution. So we're talking about moles of the solute. So therefore, I'm going to show that by saying that N1, where that's the original solution, is equal to N2, and that would be the diluted solution. When we rearrange the equation for concentration, as we have done earlier, the number of moles is equal to concentration times volume, or N equals CV. Therefore, if N equals CV, we know that N1 equals to N1 equals to N2. Therefore, it follows that C1V1, where that's the concentration and the volume of the first solution or the original solution, is equal to the concentration and the volume of the diluted solution. The relationship can therefore be used to calculate the volume to which a given solution must be diluted to produce a required concentration. So we're going to place this into action in a couple of examples. So here we're being asked to calculate the final volume of a 0.05 mole per litre. So the large M can sometimes be used to represent moles per litre. Hydrochloric acid solution that was made using 250 mils of a 10 mole per litre concentration of hydrochloric acid solution. So we know that C1V1 is equivalent to C2V2. The original solution was 10 moles per litre. The volume was 250 mils, and that was used to make up the diluted solution. So that we convert to litres. The concentration of the new solution is 0.05, which is significantly more dilute than a 10 mole per litre solution. So what we're trying to calculate is the volume of the final solution, or V2. So we rearrange the equation to show V2 as the subject. And then we input our values. So 10 by 0.25 divided by 0.05. So the volume is therefore equal to 50 litres. So 50 litres of a 0.05 mole per litre solution can be made using 250 ml of a 10 mole per litre solution of hydrochloric acid. That would probably not be really relevant for a small laboratory. However, it might be more relevant for a particular laboratory that requires a large volume of hydrochloric acid, or in industry, for example. Universities might make that amount of solution. And that brings us to the end of our concentration video, and I hope that that helps you in order to calculate your concentrations of variety of amounts and to do a few questions.